Dear friends, welcome to civilandstructural.com. To those who know about this channel and website, I need not introduce what this is all about. But for those who just type in search bar of YouTube and click down this video, I hope you get what you are searching for. And if you are feeling that this isn't sound as per your requirement, and if you are a civil and structural engineer, watch this video for a few minutes and I'm sure that you will definitely feel worth watching this video. So keep watching. So welcome again. Today we are going to have a discussion about the numerical approach to find out base pressure and effective area below the foundations, which are subjected to large biaxial moments, followed by the development of computer program for the same, which is the main purpose of this video, to spread the message, think innovative and work smart. Basically, we come across two scenarios as far as learning of the foundation is concerned. First, CG of applied loads lies in the kern zone, which I have shown here with red dotted lines. And second, CG falls beyond the kern zone. So what is the significance of this kern zone, which is shown at the middle third of this base portion? If CG lies inside the kern zone, whole area of the foundation becomes effective, remains in fully contact with soil underneath. In this case, pressure intensity at any point below the foundation can be found out with the help of simple bending equation mentioned here. And if CG falls beyond the kern zone, effective area in contact with soil gets reduced from B by L to lesser than that. In this situation, the equation mentioned here will not be valid. If CG of loads falls beyond the kern zone, there can be two possibilities. First, it will be still easy to find out the effective area and pressure below the foundations if CG deviates along the centroidal axis of the base. That means foundation subjected to large but uniaxial moments, either about x or y direction. But if the foundation is subjected to large biaxial moments, it is very difficult to find out the effective area and base pressure below the foundations. Here we can see in this slide, in case 1, CG of loads falls in kern zone. Therefore, whole area is effective and in contact with soil. In other cases, we can see portion of the footing is not in contact with soil. Effective area is not equal to B by L, but less than that. In these cases, we can see that the neutral axis of the base pressure diagram is not along orthogonal directions of the foundations, and that makes our life complicated. But some genius people worked hard to get out of this situation and made our lives easy. Here we can see in this slide, there is a graph. Someone can use this chart created by W.C. Teng. I have taken this from his book called Foundation Design. By knowing the values of EB by B and EL by L, that is the ratio of eccentricity to the respective dimension of the foundation, one can find out the value of K from this graph. Further, by multiplying this value to Q by BL, we can get the maximum pressure below foundation, where Q is vertical load and BL is total area of the foundation. And this is not the end of story. Still, we have to find out the location of neutral axis so that the volume of pressure envelope formed below the foundation will be equal to the applied vertical load, and CG of the volume envelope coincides with the CG of the applied load. For that, we need to have a iterative calculation in this case also. And this is very difficult to develop a computer program to read a graph also. And if somebody wants to do it, he has to convert these values in tabular form, and that is also cumbersome. Here we are going to discuss about a numerical approach to find out the required information. Let us consider this as a general case, and modification will be done for the other cases which we have discussed in earlier slide. Our aim is to find out the position of the neutral axis, which can give us the values of base pressure envelope, that will be equal to the total applied vertical load, and CG of pressure volume equals to CG of applied loads. Means CG of volume of pressure envelope coincides with CG of applied loads, that means eccentricity. I have seen many of people talk about finding out the CG of effective area instead of volume and compare it with eccentricity, but this is not the correct way. We have to compare CG of the volume of pressure envelope with eccentricity, that is CG of applied loads. Here I quickly want to explain you how to find out the area and volume of this yellow portion. It's simple. Effective area can be found out by deducting the area of these two small triangles from this big triangle, that is area of ECF minus area of EBC and minus area of EDH. And similarly we can find out a moment of inertia of this yellow portion also. And for volume of pressure envelope, what is this volume of pressure envelope? This is, you can see the pressure intensity at point E and F is 0, and there is a pressure intensity at C which is at maximum, and it forms a pyramid with triangular base, and the volume of triangular pyramid can be found out with the help of equation, that is 1/3 area of the base into height. And volume of this yellow portion can be found out by deducting the volume of these two small triangles from big triangles. Here we are going to change the value of A and C to find out our required solution. To achieve this algorithm for programming is to be followed. First, convert the eccentricity in positive quadrant for generalizing the case. Find out which corner of the footing are subjected to tension with the help of equation 1, which we have discussed earlier slide. Find out the location of trial neutral axis GH with the help of pressure intensities at the corners. Find out the area, moment of inertia about Na of base under compression and distance of eccentricity from this trial Na. Find out revised pressure at the corners and volume of pressure envelope and its Cg. Compare the volume of pressure envelope with applied load P and Cg of volume with eccentricity. Alter the position of Na in such a way that the error in volume and Cg converges to minimum. In this iteration, first we are going to find out three locations of neutral axis, where first there is minimum error in pressure volume, second minimum error in Cg along x direction, and third minimum error in Cg along y direction. And this is achieved by doing reduction in A and C together simultaneously. This set of locations from what we have seen in previous slide, that forms a solution band as shown here. This is, we call it as a solution band. Our required neutral axis lies in this region, bounded by the three sets of values of A and C. After finding out solution band, now F1 is fixed. We will keep F1 as fixed pivotal point, and we will alter this E1 and we will reduce A in such a way that E1 shifts towards E2. And in second iteration we keep E1 as pivotal point and we try to shift F1 towards F2 to get the neutral axis. Find and while doing this, just store all the informations regarding volume and location of CG for each and every case, and find out the location where the total error in pressure volume plus CG along X plus CG along Y is minimum. This is the procedure to be followed while doing the actual programming. Now we will start actual programming here. So first, get Excel file. Okay, I will save this Excel files as macro enabled workbook. Okay, I'll put it in study folder. I will write my data here. So first will be the foundation, width of foundation, then vertical load, moment about x-axis, moment about y-axis, eccentricity in x-axis along x, eccentricity in y, positive eccentricity. Then we will have mi, moment of inertia about x-axis, mi y. This is L, this is B, this is P, this is mx, this is my, this is xe, x, then ye, positive eccentricity. I will put the same name here, xe, ye. Okay. So here I will use a predefined set which are with me now, so that will be easy to validate our program. 5 meters, sorry, 6 meters, 5 meters, 278, 278, 250. Then eccentricity. If I consider upward y is positive and from left to right x as positive, then it will give me a positive eccentricity. Positive y will give me positive eccentricity in x direction, and here I will get a negative eccentricity along y direction for a positive mx. And I will take absolute for this is this one. I will highlight this in yellow color. So these are my inputs. And one more thing I want to do here, I will define name for these cells. Those will be very easy to write me the formulas. Okay, delete. These are my names. I would have used the same thing, same numbers, but okay. Now we have deleted. So we'll define it again. So new here, this will be L. New here, this will be B. New P for this. New XE for this. Okay, and YE for this. Okay, IX for IY for close. So IX will be L into B cube by 12, and Iy will be Q into B by 12. One more variable I want to define here, that is step, which is the incremental you can say distance at which we are going to reduce our or increase our neutral axis position. So first of all, I will find out the pressure at corners A, B and C. I will copy this sketch here for reference. I don't know why this black has come here. So initial pressures at corners at corner A, B, C, D is equal to P by A, means B into L minus, I'm talking about this corner, so X and Y both are negative with respect to centroidal axis of the uh, foundation. So P into YE divided by IX into B by 2 minus P into XE minus IY into L by 2. I will copy same formula for all, and I will change the sign with respect to coordinates. Okay. Now here for B you can see Y is positive and X is negative. For C both are positive. And for D, Y is negative, X is positive. So these are the initial pressures at the corner, and if you observe this A is negative, that means corner A is being lifted upward. So we'll identify the case over here. Case is if A and B and A is less than 0, this is less than 0, then what? It is a case 2. And if and A and D, A is less than 0 and AB less than 0, then this is a case of 3. Then if for this case only A is negative 0, then case 4. If and all the 3 are negative, B, 0, then case 5. It's a case 4. So for different cases our neutral axis cuts different edges of the foundation. So identify those edges. So neutral axis It's a trial neutral axis. Trial neutral axis cuts, Control C, it cuts to two sides of the base. So first find out, now what we'll do, I will give it's a name. New name, case. Okay. So if case 3 and 4, the neutral axis cuts to AB. If or case is equal to case 3 or case is equal to case 4, then it cuts to AB. And if or 2 and 5 but case 2 case case 5, then it cuts to BC. And for other side, if 2 and 4 or case is equal to case 2 and case equal to case 4, then it is cutting to AD. If or case equal to, what we have done, 2 and 4, so now it is 3 and 5. Case 3 case 5, then it is DC. Somewhere I have missed space here. Okay. Two, three, four, five. It is cutting at, now I have to find out where this NA is cutting to the sides of foundation. First of all, I will prepare a table over here for interpolation. AB, AC, and lengths are B, L, L, sorry, okay. Now the pressure intensities at two ends of these lines. B, B, C, E, D, D, and C. Now find out point of intersection is equal to, first I will find out ratio. This is the ratio. Just I'm applying here the properties of similar triangle here. So this into this divided by 1 plus ratio. 1 minute. 1 plus. And copy same formula for all. Now here I will put VLOOKUP. Six. Now what I will do, I will convert this intersecting point in a coordinate format. That means if I consider this coordinate as 0 0, I will find out coordinate of this point. So here I will copy this formula. If case 3 and 4, what will happen? Case 3 and 4, x will be 0. And for 2 and 5, 2 and 5, x will be the intercept. Okay. Then y for that coordinate? Same formula I will copy here. 3 and 4. 3 and 4. What will be y? Here y will be intercept. And if 2 and 5, 2 and 5, y will be 0. No, b. For second point, here we are doing nothing but writing a formula for generalizing the coordinates of this intersection point along the sides of the foundation. 2 and 4, 2 and 4, so x will be intercept. Fine. And 3 and 5, x will be L. Okay, same formula here for y coordinate. Y coordinate case 2 and 4, 2 and 4, y will be 0. And for 3 and 5, y will be intercept. Case x and y. Now what I want to do, I want to find out a and b, a and c. Which are the a and c? This. To find out a means what? Where this line cuts BC and DC. So I'm going to apply simple theory of intersection of lines here. I will first find out equation for this line, and I will put the values of x and y for this line in the equation of this line. So I will get a coordinate of intersection point. So equation of this neutral axis, that means this line, is equal to y is equal to mx plus c. y is equal to mx plus c. First case I will find out m, and then in second case I will find out c. How can I find out m? Is equal to y1 minus y2 divided by x1 minus x2. This is the slope of the line, and I will put this value in this equation to get c. So y minus m into x will give this. So this is the equation of neutral axis. So I will find out x coordinate and y coordinate where this neutral axis cuts to the extended edge DC and BC. So for equation of BC, what is the equation of BC with respect to a point as 0, 0? So y will be b. So for a, so I will put y is equal to b. So b minus c whole bracket divided by m will give me x, and for c I will put equation for this line, and equation for this line x is equal to L. So y is equal to m into L plus c. Okay, so a will be L minus this coordinate, and c will be b minus. So these are my starting values of a and c. Now what I want to do, I want to prepare a program to find out three locations of neutral axis first, and then second phase of iteration. Three locations in A for minimum delta p, minimum delta xe, minimum delta ye. For this I want to find out values of a, c, p and cg's. So here a, c, p, xe and ye. Okay, and after finding this, okay, anyway I will delete this. Okay, so first step is to find out where the error in p, x, y independently are minimum. So first I will prepare a button over here. Okay, I will define my variables. So dim as double, dim as double, dim as double, dim x as double, dim y as double. Then what else? step and A and C. Dim step as double, dim as double, dim C as double, then dim alpha. Alpha I need. Okay. Here I have taken minimum delta P, delta X, C, delta Y, A. So I have to define one set of that also. Dim delta P1 I will consider as double, delta XE1 as double, and dim delta YA1 as double. Okay. So from where we are going to get the values for these variables? So start getting those values. After definition, I will put one line to differentiate. L is equal to cells 1 4. Then B is equal to cells 2 4. Then P is equal to cells 3 4. Then XE is equal to cells positive eccentricity I will consider here 8 4. YE is equal to cells 9 4. Then step is equal to cells 12 4. After that, A is equal to cells 23 4. And C is equal to cells 24 4. Okay. Now what I want to do? I want to do the calculation. I will. So definition of variable is done. I have to start calculation with first set of A and C and want to reduce it gradually to get 3 locations of neutral axis. So I have a set of equations I have prepared for you people, and don't worry, you are going to get this set of equations from my website www.civilandstructural.com. V, then area and moment of inertia calculation. Here you can see the sorry, clearly I have found out all parameters here, and finally area, effective area I have found out by deducting those two small triangle areas from main big triangle. Similarly for effective moment of inertia also. Control C, area and moment inertia. Then volume of pressure envelope and CG. No, first base pressure, revised base pressure at corner. I have to define, no, not required to define this PA, PB, PC, because ultimately those are going to be double, because P is Z, H, Ig, which I have already converted to doubles. Volume okay. Now what I will do, I will find out the error. So delta P is equal to ABS V minus P. Delta XE is equal to ABS GX minus XE plus L by 2. Because the CG of the pyramid that we have discussed earlier, we have found out with respect to positive and that means origin in this case of calculation of CG we have considered from this to this, because A we have considered as 0 0. So to compare, to get the error, we have to add L by 2 in our eccentricity. G1 minus plus B by 2 in this case. How many times I have to do it? When the error starts increasing, that means this error is going to be decreased in successive reduction in A and C, and suddenly it start increasing, and at that moment we have to stop the iteration and we have to take that value as a our required solution. So I have to run this loop for as many as time. So for I is equal to 1 to say 1 lakh. 1 lakh is not required. When our solution is converged, we are going to get out of this loop. Okay, so first condition, if delta P is greater than delta P1, which we have already defined here, not defined, so we will define. What we can do, we define this delta P1 as initially P, delta XE is equal to XE plus L by 2, then delta YE is equal to YE plus B by 2. So this is our initial expression for delta P1, delta XE1 and delta YE1, with which we are going to compare the actual calculated delta P's. Then what is to be done? I have to write those A, C and all relevant information here in this table. Okay, so I will write down 29 3 sales 29 3 is equal to A, then sales 29 4 equal to C, then sales 29 5 is equal to V, in this case volume of the pressure, then sales 29 6 is equal to Gx minus L by 2, then sales 29 7 is equal to Gy minus V by 2. Okay, ACV okay, and one counter I want to put here. Initially I will define that counter as Q is equal to 0, R is equal to 0, S is equal to 0. Why I am using this I will explain you, or you will get to know afterwards. That is Q is equal to 1, and if If q is less than 1, then it will check for this condition, and if this condition is satisfied, then it will put q is equal to 1. And at the moment when q has turned to 1, this will not check this condition and it will go to other conditions to be checked. Then next condition I will put here, q, and here will be r delta p. Instead of delta p I will put xe1 r, and put it in next row. Okay, for third thing, yes, yes, or delta ye1. Next row is 31, 31, 31, 31, 31. And at final stage, if q is equal to 1 and r is equal to 1 and s is equal to 1, what is to be done? Exit this loop. And if, and before that I want to reduce a from a to a minus step. I think I have not defined step. I will define it again. C minus step. Let me see. Yeah, I have taken step. Okay. And what is that step? 0.002. Okay. And I will convert delta p1 equal to delta p, which is going to be taken for next iteration. Delta xe1 is equal to delta xe, delta ye1 is equal to delta ye. Then next I check whether our program can work or not. Yes, let me check these values with my data available with me. So here you can see first is error for p, that means 277.9 is very close to 278, and the position of neutral axis is at a is equal to this and c. Then next step we have found out the position of neutral axis for minimum error in xe, and that xe is 0.899, very close to 0.899. Yes, it's correct, and that is equal to a as this and c as this, and for delta ye this, and this is the value. So what I will do here, I will find out maximum and minimum of those a and c's. So is equal to, here we can see it as a solution band. Solution band. Okay, and minimum Okay, similarly I will copy for C also. Here for the second iteration, I will take A max, or how many times or how long this iteration has to go, that means second iteration. So I will find out one integer n1 is equal to, or we can say, first I will define this one, A max is equal to sales 32 3 3, then A min is equal to sales 33 3, then C max is equal to sales 32 4, then C min is equal to sales 33 4. I will find out number of iterations. N1 is equal to A max minus A min divided by step. Let me type this number of iterations, how much we need. Sales 35 1 say is equal to 1. Let's check. 266 iterations we require to be done. That is not 266 but 266 by 2, because at one time we are going to keep one point as a pivot point and find out the location. So for I is equal to 1 to n 1, for this case I want to reduce, or A you can say is equal to A max minus I minus 1 into step. Every time we are going to multiply by I to step to reduce the values of A. Then for J is equal to 1 to n1, C is equal to C max minus J times step, and start our calculation. And here calculation will be same. I will copy all this calculation here once again, but with some modification. And what modification we have to do, I will tell you. Now here I don't need this, because we have already found out 3 locations. This also I don't need. Okay. Now I want to find out the error, and that is summation of errors is equal to delta p divided by p plus delta xe divided by xe plus l by 2 plus delta ye divided by ye plus b by 2. and I want to compare this error with previous error. And previous error, let's start previous error with error 1, and that is suppose 3. Why 3? Because you see, the ratio is never going to be more than 1, all three ratios. So maximum error can be 1 plus 1 plus 1 is equal to 3. That's why I have taken initial error as 3. And don't forget to define this error 1 as double. And the error as double as well. Now, if error is less than error 1, then what are the values of A, C, P, C, G? So min A I will take as A, min C equal to C, min P equal to V, min XE equal to GX minus L by 2, min YE is equal to GY minus B by 2. Here min alpha is equal to A tan C by A. And then what I need? Effective area. Min A effective is equal to A effective. What else I need? Then error 1 equal to error, and then it will loop again. Next J, next I. Here I want to type these values in our Excel sheet. So what I will do here does not require now. So final A, final C, final P, final XE, final YE, final area, and then not final, we can see revised parameters. So here A, C, P, XE, YE, effective area, then neutral axis cuts. Okay, I will do it. 36 2 is equal to min A 37 2 is equal to min C. 38 2 is equal to min P. Cells 39 2 is equal to min XE. Cells 42 is equal to min YE. Here PA, PB, PC, PD, PC, DE 5, 36 5. Five, 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 five. Min PA, PB, PC, PD, and I will take those values also. Min PA is equal to PA. Min PB is equal to PB. Min PC equal to PC, and min PD equal to PD. Let's see. Yes, here we go. So final A is this, P is this, XE is this, YE is this. Effective area we forgot, so we'll put effective area also. 41 and 2 equal to min A effective. But instead of effective area, we put effective area percent. Divided by B into L into 100. This. Yeah, perfect. Let me check with my values. Correct, 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 correct. 77%. Yes, congratulations. You have run this program successfully. After getting the values of A and C, you can very easily find out this neutral axis cutting to which edge of the foundation, because if you see A is greater than L, then it is cutting to AB. Here in this case, if A is greater than L, then it is cutting to AB, and if C is greater than B, then it is cutting to AD, and if it is less, then it is cutting to BC and DC. And with the help of geometry, we can find out where it is actually cutting. So that's it. That is the programming we have successfully done. So conclude we can. So thank you, and thank you for watching this video. If you like this video, you can subscribe to my channel to watch more such videos, and please don't forget to share this video with your colleagues and friends. For more details, log on to www.civilandstructural.com. Thanks once again and have a nice day. Thank you very much.